Okay, picking up, we move on to the idea of indeterminacy and probability distribution. Indeterminacy has to do with being able to predict where an electron will be at a given moment based on knowing where it is and which way it's headed and how fast it's moving. The book used the analogy to a baseball catcher being able to catch the ball easily because he can see where the ball is and which way it's moving and how fast it's moving, so he knows where and when to place his glove to catch it. And of course, we all do that kind of thing all the time when we intercept a moving object in any way. The problem is that when you get down to the level of electrons, you can't really do that because, as we just established, for an electron, you can't know its location and its direction and speed all at the same time. And so that's known as indeterminacy. The position of an electron is not determined by its location and direction of travel and velocity because we can't possibly know all of those things at the same time. And in order to predict where an electron is going to be, quantum mechanics instead uses probability distributions. A probability distribution is where they take a mathematical function and they solve it for basically and use it to find basically where the locations where the electron is most likely to be at any given moment. And then they map those locations out, and those locations where an electron is most likely to be is known as an orbital. And so an orbital is really just sort of a three-dimensional probability map of where the electrons are most likely to be at any given moment. And the book shows an example of that. And the book's artistry is better than mine, so we can have a look at it. This is sort of an example of a classical Newtonian trajectory. The object is here. If you're throwing something like, say, up into the air, it's going to trace a parabolic path where it goes up, reaches a certain maximum, and comes back down again in a rather predictable way. And of course, baseball players use this when catching fly balls all the time. On the other hand, with an electron, you have to use probability maps. And you'll notice that the darkest area of the probability map is the area where the object is most likely to be found, and that corresponds more or less to this path. But it also takes into account the possibility that the electron might not follow the most likely path, and so that's the fuzzier areas on either side of the darkest part of the path. So basically, the darker the color, the more likely the electron is to be in that area at any given moment. And the lighter the color, the less likely the electron is to be in that area at any given moment. And they use that for mapping out where the electrons are likely to be in an electron. Okay, so that, and when you do that in an atom, the area where the electron is most likely to be is known as an orbital. The orbitals don't look like the path that we just saw from the book. They have different shapes, and we'll go over those in a little while. So the use of quantum mechanics in the study of the atom. Just to review, in practice, the kinetic energy, which involves velocity of an electron, is usually well known. Okay, and position is the thing that's uncertain. For each state, the energy of the electron can be stated precisely, but not the location. And so the position of an electron has to be given by a probability map of the space within the atom. Okay, and the areas with the highest likelihood of electrons, again, are known as orbitals. Okay, so as a bit of a review. The way that they determine these probability maps is by solving the Schrödinger equation. The Schrödinger equation is used to derive the energies and orbitals for electrons in an atom. The Schrödinger equation takes the form of this, which makes a lot of sense. The fancy H is known as a Hamiltonian operator. And that's just a set of operations representing the total energy of electrons in an atom. And the funny symbol, looks like a pitchfork, is the Greek letter psi. It's the equivalent to PS in English. And that is known as a wave function. And that is a description of the wave nature of electrons. And what an orbital is actually a plot of psi squared, because that's the probability. Okay, so that's used to represent an orbital. It's just basically a three-dimensional plot of psi squared. And that is your probability distribution map. Oh, and capital E, I never mentioned that, is the actual total energy of the atom. So it's the psi squared. Square of the wave function is the probability map. When mapped out in 3 dimensions, that's how you determine the size and shape of the orbitals. The most thoroughly studied element is hydrogen. because hydrogen is the simplest of the elements, of course, there's only one electron. That simplifies things quite a bit. And so the equation actually yields multiple solutions. And what that means is there are many possible wave functions. And a 3D a three-dimensional map of these wave functions will give you the orbitals for an atom. In quantum mechanics, each orbital is specified by what are known as quantum numbers. Okay, so there are three quantum numbers, and each orbital in an atom will have a unique group of those three quantum numbers. So there will never be any two orbitals in an atom that have the same values for all three quantum numbers. At least one of those quantum numbers is going to have to be different if it's a different orbital. And those three quantum numbers are n, which is often called the principal quantum number, and this corresponds to the shell number in the Bohr model of the atom. Then there is one that's called L, and that is an angular momentum quantum number. So the angular momentum quantum number. Also known as the azimuthal quantum number. And then there is M sub L. And M sub L is the magnetic quantum number. All of them, what they have in common is that the values are always integers or whole numbers. We'll see exactly what values are possible in a moment, but that's one thing that they have in common. For all of these quantum numbers, whatever value an orbital has is definitely going to be a whole number. All right, the first one. The principal quantum number, or n, is a positive integer. And it gives the relative size and energy of an orbital. Possible values for n start with 1 and go up to whatever. Theoretically, up to infinity. So again, these correspond to shells in the Bohr model. Or orbits. So, n equals 1 would be the shell closest to the nucleus, n equals 2 would be the shell second from the nucleus, and so on. And as I said, the hydrogen is the element that's been most studied. And in fact, it's the only element that they seem to have a really thorough grip on because it's only got one electron. Once you add a second electron for helium, things get way more complicated. And even today, nobody's managed to figure out even helium. But we do have a pretty good grasp on what's going on in hydrogen. The energy of an electron in shell number n, or principal quantum level n, for hydrogen is going to be RH times 1 over n squared. RH is the Rydberg constant for hydrogen. And the value for hydrogen is negative 2.18 times 10 to the minus 18 joules. And of course, n would be the number of the shell, or the principal quantum number of the electron whose energy you want to know. Notice that all of these numbers end up being negative. And we could actually even work this out a little bit. Remember, this only works for hydrogen, though. So the energy of an electron in the first shell of hydrogen is going to be negative 2.18 times 10 to the minus 18 joules over 1 times 1 over n, which is 1 in this case, squared. Well, that's just 1. So that's negative 2.18 times 10 to the minus 18 joules for an electron in n equals 1. For n equals 2, the energy would be negative 2.18 okay, times 10 to the minus 18 joules times 1 over 2 squared, which is 1 over 4. So 2.18 times 10 to the minus 18, okay, times 1/4 is negative 5.45 times 10 to the minus 19 joules. So notice that the energies are actually getting bigger as you go out from the nucleus. And it can be a little difficult to recognize because the numbers are negative, but 5.45 times 10 to the minus 19 would be a smaller number than 2.18 times 10 to the minus 18 if they were positive numbers, but these are negative numbers. And so negative 5.45 times 10 to the minus 19 is actually bigger than negative 2.19 times 10 to the minus 18. And what happens is that these values get bigger and bigger and bigger, or in other words, less and less and less negative, until at infinite distance, you reach 0 energy. And getting less and less negative means the energies are getting bigger and bigger. And when you finally get to n equals infinity, the energy would be 0. And that would be the maximum energy that an electron could have associated with an atom, although technically at infinite distance, it's not associated with the atom anymore. And the energy is negative near the nucleus because the energy of the electrons is lowered by interacting with the positive nucleus. And so remember, in chemistry, though, lower energy means greater stability. And so the electrons closest to the nucleus are the most stable. And as the electrons move further out from the nucleus, they're getting higher and higher in energy, or in other words, less and less negative in energy. And they're getting less and less stable as they move out. It's also true that the spacing and energy differences between the energy levels changes as you go out from the nucleus. Okay, so the spacing or the energy differences between the principal energy levels actually gets smaller as you go out from the nucleus. And there's a diagram on page 297, at least in this edition of the book, where you can see the difference between n equals 1 and n equals 2 is pretty big. But the difference between n equals 2 and n equals 3 is smaller. The difference between n equals 3 and 4 is even smaller. And they get closer and closer together as you go further out. And that's a function of the n squared being used as opposed to just n. If the value in the denominator were just n, then they would all be equally spaced. But it's n squared, which is why they get closer and closer together. Okay, now the second quantum number the angular momentum quantum number, or L, has values, possible values, start with 0 and go up to a maximum of n minus 1. So that's something to watch out for. L can never be any greater than n minus 1. And in fact, sometimes you can't even have 1 or 2, depending on what n is. So these numbers 1 and 2 might not even be possible. This quantum number describes the shape of the space in which the electron is most likely found. And another word for that would be, what type of orbital is the electron in? So L actually gives you the type of orbital. And the value given by L is also known as the sublevel. I think it makes more sense to me anyway to think of it though as type of orbital. Okay, so an example not only of L, but how L relates to N. If N is 1, this is for the first principal energy level closest to the nucleus, the only possible value of L would be N minus 1, which is 0. Because 0 is the minimum possible value for L, and N minus 1 is the maximum value. And in this case, they are one and the same, 0. So if N equals 1, there's only one type of orbital possible. So for N equals 1, that first principal energy level, or the first shell, if you prefer, only has one type of orbital in it. If N equals 2, then L could be 0, but it could also be 1. What this means is that the second shell, or the second principal energy level, has two possible types of orbitals that the electron could be in. If you're talking about the third principal energy level, or the third shell, the value of L could be 0 or 1 or 2. And what that means is that there are three types of orbitals in the third shell where electrons could be. And for shell number 4, the possible values for L would be 0, 1, 2, and 3. Because 3 is N minus 1, that's the maximum value for L in shell number 4. And what that means is there are 4 types of orbitals in the fourth shell. And it goes on like that, basically as far as you want to go. You can write out those numbers and find out how many types of orbitals there are in a given shell. As it turns out, the number of types of orbitals in a given shell is the same as the shell number. So notice, shell number 1, there's one type of orbital. The number for that type of orbital is not 1, it's 0, but there is one type of orbital. And for shell number 2, there's 2 types of orbital. The ones designated as 0 and 1, and so on. To avoid confusion, famous last words when you're talking about quantum mechanics, but yeah, to avoid confusion to some extent, each value of L also corresponds to a letter designation for each type of orbital. And so each number also corresponds to a letter. So if L is, and in fact, in practice, we more often use the letters to refer to the orbital type than the numbers, just again to avoid confusion. So if L is 0, that would be an S-type orbital. If L is 1, that would be known as a P-type orbital. If L is 2, that would be known as a D-type orbital. If L is 3, that would be known as an F-type orbital. If L is 4, that would be known as a G-type orbital. If L is 5, that would be known as an H-type orbital. And from here on, they go up alphabetically. We don't really do much with G and H, or actually even F for that matter. The S and the P and the D are the main focus in this class. And so those are the ones you should be most familiar with. As for the F orbitals, you should be familiar that they exist. And when we get to the part where we say how many electrons F orbitals can accommodate, you should be aware of that. But you know, that's about all you need to know about the F orbitals. But we'll go over S and P and D in some detail. But we're at 30 minutes now, so that'll be for the next segment.